All right, we're continuing to work through the Schrodinger equation for the hydrogen atom. In this video, I'll talk about the radial solutions. When we solve the Schrodinger equation for the hydrogen atom by a separation of variable techniques, it leads to the following expression. This is a differential equation which depends on the radial coordinate r. And before I get into how we solve this, I want to talk a little bit about what we might qualitatively infer from this form of the equation. So this expression inside here is sometimes called an effective potential, V effective. It has a Coulombic term and a term that's associated with the centrifugal forces that are involved, right? And what we're going to do is make a plot of V effective versus R. And what you can see at the very outset is this. There are going to be two different classes of solution, not asses of solution, although maybe, who knows. Two different classes of solutions. The first is one in which L is equal to 0. If L equals 0, there is no angular motion, and we have a purely Coulombic potential. In that case, the effective potential is going to look like this. At r equals infinity, it's going to be 0. And notice it has a negative. So as I approach 0, it's going to approach negative infinity. And here's what's important about that, right? What you might infer from this is that in this scenario, where L is equal to 0, the electron is going to hang out where the potential is the lowest, right? That is at the origin. Now, the other type of solution we're going to get is when L is not equal to 0. In that case, it's going to have both an angular motion and a Coulombic contribution. And so I need to think about both the Coulombic and what this expression looks like. And this one is a 1 over r squared. So again, at infinity, it's going to be 0. And as I approach the origin, it's going to increase to positive infinity. This is some expression which is proportional to 1 over r squared. I now add these two together. Here it's 0, 0, 0, 0, and it's going to start to dip down, right? Following this 1 over r potential. But what's going to happen is that as I approach the origin, this 1 over r squared beats out the 1 over r. It becomes a limit. And so initially it's going to drop, and then it's going to start to increase. So this is a scenario in which L is not equal to 0. And what you can see in this solution is that the electron hangs out here, away from the nucleus. And specifically, because this effective potential is going to infinity, right? You see that the electron is never at the nucleus. So I might infer these two different kinds of solutions that exist to the radial expression. All right. This problem can be solved. And if you solve it, here are the solutions. It looks complicated, so let me kind of walk you through this. The first is that you'll see this is labeled by two quantum numbers, n and l. So there are two quantum numbers associated. N is called the primary quantum number, and it has values 1, 2, 3. L is called the orbital angular momentum quantum number, and it has values n minus 1, n minus 2, n minus 3, dot, 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 all the way to 0. This L is the same L as we saw in the spherical harmonic half of it. They arise in both equations because of the separation of variables. And now all of these variables are interrelated. N determines L determines M. The radial solution is written as a function of rho. Right? So rho is a reduced variable, R divided by A naught. We saw this in the harmonic oscillator when we had the Y equals X divided by alpha. And like the harmonic oscillator, there are also multiple parts to this solution. So let me show you these. The first is a normalization constant. Okay. Again, this depends on n and l, so it's adjusting the amplitude of the function. The second are these terms here, r times L of rho. And again, this means L as a function of the variable rho, not L times rho. These are some polynomial. And we'll talk about that more in a second, but it's some polynomial in the variable rho. Last but not least, I get an exponentially decaying function. There's some exponential decay associated with these. What is this polynomial L? Well, in the case of the harmonic oscillator, we had Hermite polynomials. In the case of the rigid rotor, we had Legendre polynomials. In the case of the hydrogen atom, we have Laguerre polynomials, right, capital L. So Laguerre polynomials are solutions to this general differential equation. Right? They look like this. They have this indexed form. Right? You'll notice that they sort of stretch out in space. So the lowest one, L equals 1, is just a straight line. L equals 2 is a parabola. L equals 3 is a cubic, et cetera, et cetera, et cetera. And at the end of the day, if I take all of these things and I put them together, I get the hydrogen radial wave functions. Now, you can look at these in the video, but check out the handout on Canvas. Right? That's where you should see these, and I've tabulated them for you here. One quick note, and then we're going to talk about these solutions. If you look at the expression that I just gave you for the radial function, it has this form. And if you're looking carefully at Atkins, you'll see it has this form. And you'll note that these are slightly different. Right? Atkins defines rho in this way. I have defined rho in this way. And because it is defined differently, the radial solutions have different forms. Now, this may stress you out. Right? I'm showing you explicitly that difference here. These are the radial functions that I gave you. These are the ones listed in Atkins. At the end of the day, right, you can use either of these two forms. Right? They're actually equivalent, but you just need to make sure that you are defining your variables rho correctly. Right? And if you do that, you'll be okay. All right, I'm going to stop here, and I will put up another video about what these solutions look like. See you then.